Well, I now have the pleasure of introducing Dr. William Rhodes, who's going to welcome you on behalf of NNSA. Bill's a staff member at NNSA supporting global security issues. He's served as the Federal Program Manager within the Defense Programs Office of Research and Development for Primary Assessment Technologies. Before joining NNSA, he was a research scientist at Savannah River National Laboratory. He served as a nuclear analyst supporting the U.S. Navy nuclear propulsion program prior to his stint at Savannah River. So I would like to welcome Dr. Rhodes.
Okay. Thank you very much for the gracious introduction. My name is Bill Rhodes. I'd like to welcome everyone here this morning. I'm a general engineer with NNSA, and there are a lot of questions as to what a general engineer is. It's very interesting. I started my career at Exxon Research over 30 years ago, and in private industry, you don't find anyone who has a title of a generalist. They're all very specific technology-driven scientists, but I think general engineer is kind of interesting. It requires one to look at multiple disciplines and very interesting and diverse ways and methods to solve very challenging problems. So welcome on behalf of Dr. Kathy Alexander, the Assistant Deputy Administrator for Research, Development, Test, and Evaluation at the National Nuclear Security Administration, Department of Energy. I have the distinct pleasure and honor to provide the welcome address to a very distinguished crowd of individuals to the 2015 Annual Program Review of the DOE NNSA Stewardship Science Graduate Fellowship Program. Kathy sends her regards and is currently traveling back from Nevada. She will be here this evening to provide an address to open up the Fellows Poster Session. The Stewardship Science Academic Alliances were originated and inaugurated in 2002 by the National Nuclear Security Administration to enhance the connections between NNSA laboratories and the activities of university scientists and their students in research areas important to NNSA. These include low energy nuclear science, properties of materials under extreme conditions, and hydrodynamics, and very recently we've added radiochemistry to the portfolio. An integral component of SSAA is the support of the Stewardship Science Graduate Fellowship Program. These fellowships were established to attract highly skilled and talented students to the noted areas of study. And as I read that this morning, and as I recalled looking at the number of applications and the awardees, the term highly skilled and talented students really is an understatement. Everyone who applies to the program is highly talented and highly skilled. So you folks are indeed the cream of the crop, the 1%ers, so congratulations on being part of the program. It will definitely carry over for the rest of your careers, and it will be a highlight even when you get to my age to recall your experiences both in your field of study at the university, but also, and probably more particularly, your interactions at the laboratories. You will find, if you've completed your 12-week practicum, that working at a DOE National Laboratory is very challenging, it's very interesting. There are rules that will seem challenging, but you get to apply science to fields of study that people in the private industry would never have the opportunity to look at. I don't want to put down private industry. I worked in private industry for a number of years. I also supported the Naval Nuclear Propulsion Program for a number of years. But at the DOE National Laboratories, you are given a key to investigate science. And you get to have that key to investigate science for the sake of studying science. So that's a very unique opportunity that the rest of the world doesn't get to experience. Over the next 2 days, you'll find yourselves immersed in a vast array of science and technology and on tap to present your latest and greatest findings to your peers and yes, your sponsors. And you will hear the experience of those who have worked at the labs and your colleagues who have completed a 12-week practicum in residence at a particular NNSA laboratory engaged in applied research. So by now you've heard the quote, I'm sure, by William Butler Yeats, that education is not the filling of a pail, but the igniting of a fire. But does it stop there? Once the fire is lit, what does it really mean to call oneself a scientist? Again, is the fire enough to be a good scientist? I assert that it's not. There are probably many answers to the question as to what a scientist is, and everyone probably has their own definition and their own mindset. But I recall, and I actually applied the technique that was discovered in 1959, known as the Moosbauer effect. And it's a physicist phenomenon, and many of the folks in the audience here are physicists, so I'm sure many of you have heard of this, and some perhaps have used it in your field of study. It basically is a method of probing solids and has applications to magnetism, metals and alloys, chemical compounds, biological molecules, geology, archaeology, and other sciences. This outstanding discovery was made by a young physicist in Germany by the name of Rudolf Moosbauer. And it was discovered while he was working on his PhD thesis. So he's about your age. What he discovered was a recoilless nuclear resonance fluorescence of gamma radiation. At the time, back in the late 1950s, it was thought impossible for nuclei to absorb and emit gamma rays resonantly. But when embedded in a lattice, the recoil due to gamma rays may in fact become taken up by the entire solid, making the energy loss negligible, permitting recoil-free nuclear resonance emission and absorption. This is a clear case of matter-radiation interaction, maybe not at extreme conditions, but perhaps under the extreme duress of a struggling graduate student. For this, he was awarded the Nobel Prize in Physics in 1961. He was one of the youngest recipients of this most prestigious award. This discovery led to the development of new techniques for the measurement of hyperfine interactions between nuclear moments and electromagnetic fields. The method yields information for a diverse array of disciplines, providing information on the valence states, symmetry, magnetic behavior, phase transition, lattice dynamics, and other solid-state properties. It was this very technique that allowed me, a struggling graduate student over a decade ago, to uncover previously unknown surface reconstruction phenomena of a tin platinum heterogeneous catalysis system that was operated under realistic conditions in what we refer to as operando systems. For those of you that are not heterogeneous catalysis experts, I could tell you that materials aging for a heterogeneous catalysis system under realistic reaction conditions is definitely a phenomena that occurs on the order of milliseconds. The surface reconstruction for heterogeneous catalysis, especially for binary elements, happens all the time, and one cannot assume that the surface at the beginning of the chemical reaction is what you end up with when you have several hours of time on stream, and you must understand those changes to really understand at a molecular level what's going on with your heterogeneous catalysis system. So my PhD was saved with this wonderful technique and some very interesting and colorful Hungarian scientists that allowed me to perform the work over in Hungary. But his discovery was anything but straightforward. Discoveries usually are not straightforward. Indeed, Moosbauer chose to work in the field of resonance fluorescence of gamma radiation, studying nuclear resonance absorption with the 129 keV gamma radiation of iridium-191. His hypothesis was very simple. He selected an effective method to decrease the overlap of the Doppler-Broaden emission and absorption lines, theoretically increasing the transmission intensity by cooling the absorber. What he measured, though, was the opposite effect. He measured a decrease instead of an increase in the transmitted intensity by 1 part in 10,000. So back in 1959, 1958, in the late 1950s, one would typically assume that that wrong sign of 1 part in 10,000 was due to an error in his equipment setup, and he spent over a year in efforts trying to find and eliminate the possible sources of error. He built the entire apparatus himself and was acutely aware of the electronics and the temperature control systems. He collected enough statistics for, in effect, 3 times the standard deviation, but nevertheless, he was convinced for a long time that there's something wrong with the sign, 1 part in 10,000. But he didn't give up. After a year's worth of effort, probably 52 weeks of meetings with his advisor, reporting no progress to date, the sign's still wrong, he sat back and he said to himself, perhaps there must be some sort of strange phenomena responsible for the wrong sign of the absorption effect. He developed a theoretical explanation, and he wrote of the observed phenomena. He published a paper, his first paper, and then he left Heidelberg, where the work had been done, in order to fulfill his requirements to complete his PhD in Munich. 3 months later, he was, according to his memoirs, he was relaxing in Munich with a cup of tea, and he received his first manuscript in the mail, and he sat back and he was reading it with full pleasure, his first manuscript in print form. And after 15 minutes of reading his manuscript, he dropped his cup of tea, shattered the crystal everywhere, and jumped up and realized that a most simple and beautiful experiment had yet to be done. He realized that he could just do a simple Doppler shift experiment, and he could verify the lines of natural width directly. In other words, the simple and most spectacular experiment had been forgotten and was probably done by one of his contemporaries in a competing laboratory. So he raced aboard the train to Heidelberg, and on his way to the train, he stopped in a toy store and bought some tooth wheels from a toy shop to do some rotor-type velocity spectrometry when he got to Heidelberg to do his Doppler shift experiments. And the Doppler shift for most of our techniques is about orders of centimeters per second, so you could do a simple experiment. And with the Doppler shift experiment, the effect would be 1 in 100. When he put his apparatus, his little toy gadget together for this little his rotor-type velocity spectrometer, the phenomena showed up in full beauty. Today, most bar spectroscopy is developed into a standard laboratory tool and is used in many fields. There are more than 1 million most bar data records present in public papers and books, and the number is increasing every day. I hope, Musbauer noted in his memoirs, that we will all continue to have fun in lifting, little by little, Mother Nature's important and not so important secrets. Perhaps we're in for other surprises. Thank you very much, and enjoy your next 2 days.